Hello everyone, my name is Sam. Welcome back to CPP Under the Microscope. Today we are diving into one of CPP's most confusing syntaxes, auto double ampersand, or auto rref. At first glance, it looks just like any other way to write an rvalue reference, but it's actually a trap. It's not always an rvalue reference. It's something much more flexible and dangerous. In this video, we will demystify what auto double ref really is, a forwarding reference, also called universal reference, see how it deduces differently for lvalues and rvalues, look at the assembly generated for the same template function called with an lvalue versus an rvalue, and watch the copy constructor versus move constructor get code. And finally, I'll show you some common pitfalls and when you should actually use auto rref. Let's jump in. Before we get into auto rref, let's quickly recap lvalue and rvalue references. Lvalue references bind to objects that have a name, like x. Rvalue references bind to temporaries like 20 and enable move semantics. Now, what happens if we use auto rref? Intuitively, you might think R1 is an rvalue reference, but it's not. Auto double ampersand is a forwarding reference. It deduces its type based on what you initialize it with. If you give it a nil value like x, auto deduces to an lvalue reference. It deduces to int ampersand. Then reference collapsing turns auto double ampersand into int ampersand. If you give it an r value like 20, auto deduces to a non-reference, so int, and auto double ampersand becomes int double ampersand. So R1 is actually an lvalue reference, and R2 is an rvalue reference. But here's the kicker. R2 is typed as int double ampersand, but the variable R2 itself is a nil value because it has a name. So we'll come back to that a little bit later. Now let's see why this deduction matter. We use a simple widget class that works when it's copied or moved. It is our widget class. It has 3 constructors, one default one, which prints base constructor, copy constructor, which prints copy, and move constructor, which prints move. And add a template function relay that takes a forwarding reference and constructs our local widget. Here is the template function. Now let's call it 2 ways. When you run this, you see copy for the first call to relay here and move for the second. That's because auto rref, and in our case is trref, deduces to widget ampersand for w here and to widget for the temporary. We can also write template function in another way after C++20. Let's do it. Like this. This again a templated function, but seeing is believing. Let's look at the assembly. I'm using Compiler Explorer. First, the code to relay w. In the assembly, we see This is the generated function, and this is the call to widget, and it uses the copy constructor because arc was detected as widget reference, so we copy. Now let's look at array widget, this function call here. Here we can see that the move constructor is used. The temporary is treated as an rvalue, so we move. The same template function, but the generated code is different, all because the way auto rref deduces, that's the power of forwarding references. Now let's look closely inside relay. This std forward is doing something crucial. Remember earlier I said that even if arc was passed as an rvalue, inside the function it becomes an lvalue because it has a name. That's a problem. We'd lose the move semantics. This is exactly what std forward solves. It's a conditional cast. If t is an lvalue reference, std forward returns an lvalue reference. If t is a non-reference, meaning the original was an rvalue, it returns an rvalue reference. Here is the classic example straight from cppreference. The documentation explains it perfectly. If a call to wrapper passes an rvalue as the string, then t is deduced to as the string, not as the string reference, const as the string reference, or as the string double reference. And sd forward ensures that an rvalue reference is passed to foo. If call to wrapper passes a const lvalue as the string, then t is reduced to const as the string reference, and sd forward ensures that a const lvalue reference is passed to foo. And if a call to wrapper passes a non-const lvalue as the string, then t is reduced to std string reference, and std forward ensures that a non-const lvalue reference is passed to foo. Without std forward, we would always get an lvalue reference, meaning we'd always copy, never move. That's why std forward is essential for perfect forwarding. But here is where people get tripped up. Even if auto rref deduces to an rvalue reference, the variable itself is an lvalue. Let me show you. First notice widget rref. We're not creating a new object here. Rref is just a reference, an alias for w. That means no constructor is called at this point. We use std move w because rref is an rvalue reference, and rvalue references can only bind to rvalues. Without std move, this wouldn't compile. Let's check this. Here it is, rvalue references to type widget cannot bind to lvalue of type widget. Even though rref is declared as widget double ampersand, the variable itself is a named variable, so it behaves like an lvalue in expressions. Here is the example. Because rref is an lvalue, assigning it to a triggers the copy constructor, not the move constructor. And we can see it here. Here we explicitly cast rref to an rvalue using std move. Now the move constructor runs, transferring resources instead of copying them. We can see it here. So the key points. Binding a reference doesn't construct a new object, as we can see here. This base constructor was called when this line executed. Sd move is needed to bind lvalues to rvalue references. Named rvalue references are lvalues, so you need sd move again to actually move from them. Another common place you see auto double ampersand is in a range-based for loops. Many people use, for example, or const auto ref, but actually auto double ampersand is the safest and most efficient. Now let's see an example of that. Create a vector with two widgets inside it. As you can see, these are the base constructors from this one here. Then the vector copies them. But with auto double ampersand lm, we don't see any copy or moves here. But if we, for example, do this, we can see an extra two copies, which depending on the case can be expensive. But if you use, for example, auto ampersand lm, you don't get these copies, but now it won't bind to temporary containers or proxy objects. Now let's check an example with proxy objects. As we can see, this compiles. If we check the assembly for this one, it is doing a bit twiddling, but auto double ampersand handles it seamlessly. If we remove and just use this, it will not compile. As you can see, non-const lvalue reference to type reference, aka bit reference, cannot bind to temporary of type reference. When you should actually use auto double ampersand. In range-based for loops, use auto double ampersand for maximum safety. It handles proxies and avoids copies. In generic code, templates wonders use auto double ampersand plus std forwarding to perfect forward arguments. In normal code, stick to auto ampersand or const auto unless you have a specific forwarding need. Remember, auto double ampersand is a tool, not a toy. It's there to preserve value categories in generic contexts. Let's recap. Auto double ampersand is a forwarding reference deducing to lvalue reference for lvalues and rvalue reference for rvalues. The same template function can generate different constructor calls. We saw it in assembly. As the forward is the magic that preserves the original value category. But the variable itself is always lvalue, so you need std_move to actually move. Hit like and subscribe. Thanks for watching. See you in the next one.